Section 6.1, Day 2, Discrete and Continuous Random Variables. After today's lesson, you should be able to calculate and interpret the standard deviation, as well as the variance of a discrete random variable, and describe continuous random variables. First off, let's review what a discrete random variable is. If we can find all ways to list all possible outcomes for a random variable and assign a probability to each one, we have what's known as a discrete random variable. Since we use the mean as a measure of center for a discrete random variable, which we found in yesterday's lesson, we'll use the standard deviation as our measure for spread. The definition of variance of a random variable is similar to the definition of variance for a set of quantitative data that we did back in Chapter 1. Our definition of variance. Suppose that x is a discrete random variable whose probability distribution is given. And we know that the mean, mu sub x, is the mean of the random variable. The variance of x is given by this following formula. Remember, sigma squared is our sign for variance, and sub x means we have it for a random variable x. And it's equal to taking each individual observation, subtracting the mean that we've calculated, squaring that, multiplying it by the probability for that single value, and doing that for every outcome from our random variable, and adding those together. So in short notation, the variance will equal the sum of all the individual outcomes minus the mean of the random variable squared times each of those probabilities. To get the standard deviation of a random variable, then it's simple. We just take the square root of the variance like we did earlier. If you remember yesterday, we were working with APGAR scores as they related to a healthy child. Here was our discrete random variable for the scores from 0 to 10. Now I want to compute the standard deviation of the random variable x and interpret it in context of the problem. So again, our formula is the variance will equal the sum of each individual x minus the mean squared times the probability of that outcome. If you remember from yesterday's PowerPoint lesson, the mean of this random variable was 8.128. So in going through this, the first value I have in my calculation from the variance will come from 0 minus my mean of 8.128 squared times the probability of getting a 0, which is 0.001. I would then do that for all of the possible outcomes, add those together, and my variance ends up being 2.066. Again, this is variance. I want the standard deviation, so it's as simple as taking the square root of that value, which ends up being 1.437. Again, anytime you see in context, I need to relate it back to what the problem is dealing with. I can't just say the standard deviation is 1.473. So in context of the problem, I would say the standard deviation of x is 1.437. So what that means is, on average, when I randomly select a baby's APGAR score, it will differ from the mean by about 1.4 units. To finish up section 6.1, we need to cover continuous random variables. Everything in our discussion thus far from this section has been about discrete. Discrete random variables, again, commonly arise from situations that involve counting something. Situations that involve measuring something often results in what's known as a continuous random variable. A continuous random variable x takes on all values in an interval of numbers. The probability distribution of x is described by a density curve. Now remember, for a density curve, the area underneath the curve must be equal to 1. The probability of any event is the area under the density curve and above the values of x that make up that event. The probability model of a discrete random variable x assigns a probability between 0 and 1 to each possible value of x. In a continuous random variable y, it'll have infinitely many possible outcomes. All continuous probability models assign a probability of 0 to every individual outcome. Only intervals on a continuous random variable have values with a positive probability. So here's an example. If you read the example on page 351, you're going to define y as the height of a randomly chosen young woman. Y is a continuous random variable whose probability is a normal distribution with a mean of 64 and a standard deviation of 2.7. I want to know what the probability that a randomly chosen young woman has a height between 68 and 70 inches. This should be very familiar to what we did when we did normal calculations earlier. Here's a picture, and I have a normal distribution with a mean here of 64, and the standard deviation is 2.7. I want to find the probability or the area under the curve that lies between 68 and 70. So you can see the shaded region here on my distribution. So I'm going to standardize this. And remember my standardizing formula to find z. Z is x minus mu divided by sigma. But now since I'm dealing with a discrete random variable, it's going to be x minus mu sub x, and mu sub x is the mean of my continuous random variable, divided by sigma sub x, which is the standard deviation of my continuous random variable, which are given here. So when I standardize 68, I end up with a standardized value of 1.48. Standardizing 70, I end up with a standardized value of 2.2. So to find the area under the curve here, I'm going to find the probability that z is less than or equal to 2.22 and subtract from that the probability that z is less than 1.48. Using the z-table, a z-score of 2.22 has a probability value of 0.9866, and a z-score of 1.48 has a probability of 0.9306. And subtracting those, I end up with 0.0562. In context of the problem then, that means there is about a 5.6% chance that a randomly chosen young woman will have a height between 68 and 70 inches tall. Really, this is nothing more than what we had done with normal calculations before. In summary, reviewing discrete and continuous random variables. A random variable is a variable that takes on numerical values determined by the outcome of some chance process. The probability distribution of a random variable x tells us the possible values of x and how the probabilities are assigned to those values. A discrete random variable has a fixed set of possible values with gaps between them. The probability distribution assigns each value a probability between 0 and 1 such that the sum of the probabilities must be 1. And a continuous random variable takes on values in some interval of numbers. A density curve describes the probability distribution of a continuous random variable. When we calculate the mean of a random variable, it is the long-run average value of the variable after many repetitions of a chance process. It also is known as the expected count of the random variable. To calculate the expected count, or the mean, mu sub x, remember it's equal to the sum of each individual outcome times its probability. The variance of a random variable is the average squared deviation from the values of the variable from their mean. The standard deviation is the square root of the variance. For a discrete random variable x, remember variance is calculated by taking each individual observation minus the mean squared times the probability of that outcome. And again, it's the sum of all of those. So you're going to do that for each individual outcome and add up the results. The standard deviation then would be the square root of that.